Close your eyes for a moment. Think about time. Right now, in this instant, you exist in what we call the present. A second ago is gone, vanished into the past. A second from now hasn't happened yet, it waits in the future. This seems obvious, doesn't it? Time flows forward, always forward, like a river that never reverses course. Except, what if I told you that's not quite how time works? What if I told you that according to our best understanding of physics, time is not a river at all, but rather a dimension, a fourth dimension, as real as length, width, and height? What if I told you that Einstein's equations, the very mathematics that describe gravity, black holes, and the expansion of the universe, contain within them the possibility of time travel? Not the magic of science fiction, not the fantasy of movies and novels, but actual, mathematical, perhaps theoretically possible time travel. Tonight, we're going to explore one of the most fascinating questions in all of physics. Is traveling through time scientifically possible, or is it forever beyond our reach? We'll journey through Einstein's revolutionary insights about the nature of time itself. We'll peer into the mathematics of wormholes, bridges through the fabric of spacetime that might, just might, allow a shortcut, not just through space, but through time. We'll grapple with the paradoxes that arise when past meets future, and we'll explore the cutting edge of modern physics, where quantum mechanics and general relativity collide in attempts to understand whether the universe permits us to bend time itself. This is a journey that will take us from the familiar ticking of clocks to the warped space-time near black holes, from the smallest quantum scales to the largest cosmic structures, from rigorous mathematical physics to profound philosophical questions about the nature of reality. So, settle in, get comfortable, let your mind expand to consider the impossible or the just barely possible, because tonight we're going to travel through time together. Even if we never leave this moment, we're going to understand time in ways you never have before. The journey begins not with time machines or wormholes, but with a simple question that started a revolution. What exactly is time? For thousands of years, humans thought they understood time pretty well. Time was absolute, universal, the great cosmic clock that ticked the same for everyone, everywhere, always. When Isaac Newton formulated his laws of motion in the 1600s, he described a universe that ran like perfect clockwork. Time was the backdrop against which all events unfolded, flowing uniformly from past to future at the same rate for everyone and everything. In Newton's universe, time was simple. If an event happened at noon in London, it happened at noon everywhere in the universe, at least in principle. If you could account for the differences in location, time was independent of space, flowing eternally forward, the same for all observers, never varying, never bending, never doing anything unexpected. This view of time felt right. It matched our everyday experience. When you and I look at our watches, they tick at the same rate. When we agree to meet at 3 p.m., we both experience the passage of time from now until then in the same way. Time is the one thing we all seem to share equally. And then came Albert Einstein. In 1905, a 26-year-old patent clerk in Switzerland published a paper that would shatter this comfortable understanding. The paper was titled On the Electrodynamics of Moving Bodies, but we know it now as the special theory of relativity. And buried within its mathematics was a truth so strange, so counterintuitive, that it took decades for even physicists to fully accept it. Time is not absolute. Time is not universal. Time is not the same for everyone. Time, Einstein showed, is relative. The insight started with light. For decades, physicists had been puzzled by a strange experimental fact. No matter how you measure the speed of light, no matter how fast you're moving when you measure it, you always get the same answer. Light always travels at exactly 299,792,458 meters per second. Always, without exception. This is weird. Think about it. If you're standing still and a car drives past you at 60 miles per hour, that's the speed you measure. But if you're driving at 60 miles per hour in the same direction, the car appears to be standing still relative to you. Speed is relative to the observer. Light doesn't work this way. If you're standing still and light passes you, you measure it traveling at the speed of light. If you're moving at half the speed of light in the same direction as a beam of light, you might think the light would appear to be moving only half as fast relative to you. But no, you still measure it traveling at exactly the speed of light. How can this possibly be true? Einstein realized that for this to work, something else had to give. If the speed of light is constant for all observers, then something else must be changing to make the math work out. What changes, he discovered, is time itself. Space and time, Einstein showed, are not separate things. They're woven together into a single, four-dimensional fabric called spacetime. We live not in 3 dimensions of space plus 1 dimension of time flowing independently. We live in 4-dimensional spacetime, where space and time are intimately connected, inseparable, unified. And here's where it gets truly strange. The rate at which time passes depends on how you're moving through this 4-dimensional space-time. Move faster through space, and you move slower through time. Find yourself in a strong gravitational field, and time slows down for you relative to someone far from that gravity. This isn't an illusion. This isn't a trick of perception. Time genuinely, physically, measurably passes at different rates depending on your motion and your position in a gravitational field. You and I do not experience the passage of time at the same rate unless we're moving at the same velocity and experiencing the same gravitational field. 10 years later, in 1915, Einstein extended these ideas into what he called the general theory of relativity. This theory showed that gravity itself is actually a warping of spacetime. Mass and energy curve the fabric of spacetime, and objects moving through this curved spacetime follow curved paths that we perceive as gravitational attraction. A planet orbiting a star isn't being pulled by a force reaching across empty space. Rather, the star's mass warps spacetime around it, creating curves and valleys in the 4-dimensional fabric, and the planet simply follows the straightest possible path through this curved geometry. We call that path an orbit, and in regions of extreme curvature near massive objects or in intense gravitational fields, time itself bends and warps. Time passes at different rates, depending on how deeply you're situated in a gravitational well. This is not speculation. This is not untested theory. We've measured it, we've confirmed it. Atomic clocks on airplanes tick at slightly different rates than atomic clocks on the ground. GPS satellites orbiting Earth have to constantly correct for the fact that time passes slightly faster for them than it does for us on the surface. We've measured time dilation between atomic clocks separated by less than a meter in altitude. Time is flexible. Time is variable. Time is a dimension of space-time that can be stretched and compressed by motion and gravity. And if time can be warped, could it be traveled through? The answer is yes. In fact, you're already doing it. Let me tell you about 2 twins. They're born at exactly the same moment, identical in every way. Let's call them Alice and Bob. On their 20th birthday, Bob decides to become an astronaut. He boards a spacecraft capable of traveling at extremely high speeds, say 90% the speed of light. He embarks on a journey to a distant star system 20 light years away. Alice stays on Earth. From Alice's perspective, watching from Earth, Bob's journey takes a long time. 22 years to get there, and another 22 years to return. When Bob arrives back on Earth, Alice is 64 years old. She's lived 44 years since Bob left. But here's the strange part. Bob hasn't aged 44 years. Due to the effects of time dilation, the slowing of time for objects moving at high velocities, Bob has aged only about 19 years. He steps off his spacecraft at age 39. His twin sister is 64. This isn't a trick. Bob hasn't traveled faster than light, he's obeyed every law of physics. But he has traveled into Alice's future. He left when they were both 20, and he returned to find his sister in her 60 seconds while he's still in his 30 seconds. Bob has time traveled. Not dramatically, not centuries into the future, but genuinely, measurably, physically into his sister's future. The mathematics behind this is precise. Time dilation due to velocity follows a specific equation involving the Lorentz factor, which depends on the ratio of your velocity to the speed of light. The closer you get to light speed, the more extreme the effect becomes. At 90% light speed, time passes about 44% as fast for you compared to a stationary observer. At 99% light speed, time passes about 14% as fast. At 99.99%, time passes at just 1.4% of the normal rate. If Bob could somehow travel at 99.99% light speed for what felt to him like 1 year, Alice would age about 70 years. When he returned, he'd be 1 year older. She'd be 7 decades older. We've seen this effect in reality, not with humans traveling on spacecraft, but with subatomic particles. Muons, a type of unstable particle created when cosmic rays strike Earth's atmosphere, normally decay in about 2 microseconds. At rest, a muon would barely have time to travel 600 meters before decaying. Yet we detect muons from the upper atmosphere reaching Earth's surface, traveling tens of kilometers. How? They're moving at nearly the speed of light. From our perspective, they live much longer than 2 microseconds because of time dilation. From the muon's perspective, if we could imagine such a thing, they still live 2 microseconds. But the distance to Earth's surface is contracted due to the relativistic effects of their high velocity. In particle accelerators, we routinely accelerate particles to velocities where their lifetimes are extended by factors of 29 or more. In experiments at CERN, muons moving at velocities where gamma equals 29.327 lived 64.378 microseconds instead of their normal 2.2 microseconds. The extension factor matched predictions to within 0.1%. This is time dilation due to velocity. It's real. It's measured. It's an inescapable consequence of living in a universe where the speed of light is constant for all observers. But there's another type of time dilation, one that doesn't require motion at all. Gravity slows time. This was Einstein's insight in general relativity. The stronger the gravitational field you're in, the slower time passes for you relative to someone in a weaker gravitational field. This is gravitational time dilation, and it arises from the fact that gravity is actually the warping of space-time by mass and energy. The mathematics predicted this in 1915, but it took decades to measure it with sufficient precision. The first direct experimental confirmation came in 1959 with the Pound-Rebka experiment, which measured the tiny frequency shift of gamma rays traveling up and down a 22.5-meter tower at Harvard University. The gamma rays traveling upward against Earth's gravity were redshifted. Their frequency decreased in exactly the amount predicted by gravitational time dilation. Since then, we've measured it with increasing precision. In 2010, scientists at the National Institute of Standards and Technology measured gravitational time dilation over a height difference of just 33 centimeters, about 1 foot. 2 atomic clocks, one placed a foot higher than the other, ticked at measurably different rates. The difference was tiny, about 90 billionths of a second per day, but it was real, and it matched Einstein's predictions perfectly. In 2022, researchers pushed this even further, measuring time dilation between 2 parts of a single cloud of atoms separated by just 1 millimeter, 1 millimeter, the width of a sharp pencil tip. And even over that tiny difference in height, time passed at detectably different rates. Think about what this means. Right now, as you lie in bed or sit in your chair, time is passing slightly faster for your head than for your feet. The difference is infinitesimal, you'll never notice it in a lifetime. But it's real. Your head is aging faster than your feet by a few billionths of a second per day because your head is slightly farther from Earth's center of mass and therefore experiences slightly weaker gravity. Earth's core, some 6,400 kilometers below the surface, experiences stronger gravity than the surface does. Over the 4.5 billion years of Earth's existence, time has passed more slowly at the core than at the surface due to this stronger gravitational field. The accumulated difference is about 2.5 years. Earth's core is, in a very real sense, 2.5 years younger than its surface. The global positioning system depends on accounting for gravitational time dilation. GPS satellites orbit at about 20,000 kilometers above Earth's surface, where Earth's gravity is weaker. Clocks on those satellites run faster than identical clocks on the ground by about 45 microseconds per day. If we didn't correct for this, GPS coordinates would drift by about 10 kilometers per day. Your phone's ability to pinpoint your location depends on the fact that Einstein's predictions about time dilation are correct. The effect becomes more extreme in stronger gravitational fields. Near a neutron star, where gravity is millions of times stronger than Earth's, time dilation becomes dramatic. An hour near a neutron star's surface might correspond to days or weeks for someone far away. And near a black hole, time dilation becomes extreme beyond imagination. Imagine approaching the event horizon of a stellar mass black hole, one with a mass perhaps 10 times that of our Sunday. As you fall inward, accelerating under the black hole's immense gravity, you look back at the universe you're leaving behind. You see stars, galaxies, the whole cosmos, and you see it speeding up. From your perspective, time for the outside universe is passing faster and faster. Events that would take years are compressed into moments. Stars are born and die in what seems like seconds. As you approach the event horizon, that point of no return beyond which not even light can escape, the outside universe appears to race forward at an ever-increasing rate. To you, nothing special happens at the event horizon itself. You pass through it smoothly, perhaps not even noticing the moment you cross it. But from the perspective of someone far away, watching you fall, they never actually see you cross the horizon. Instead, they see you slow down as you approach it, your image becoming increasingly redshifted, dimmer and dimmer, frozen in time at the edge of the black hole, asymptotically approaching the event horizon but never quite reaching it. To them, you take forever to reach the horizon. To you, you fall through in finite time. Both perspectives are equally valid. This is what relativity means. The passage of time is relative to the observer. At the event horizon of a black hole, time from the perspective of a distant observer essentially stops. A clock at the horizon would appear frozen to someone far away. You are already a time traveler. Every moment, you move forward through time at the rate of 1 second per second in your own reference frame. But speed up or move to a location with different gravity, and you'll move through time at a different rate compared to others. Time travel to the future isn't just possible, it's mandatory. We're all doing it. Right now. Constantly. The question is, can we travel to the past? In 1916, just months after Einstein published his general theory of relativity, a German physicist named Karl Schwarzschild did something remarkable. While serving in the German army on the Russian front during World War I, suffering from a painful autoimmune disease that would kill him within the year, Schwarzschild solved Einstein's field equations exactly for the case of a non-rotating spherical mass. His solution described something that wouldn't be called a black hole for another 50 years, but that's exactly what it was. A region of space-time so intensely warped that nothing, not even light, could escape from within a certain radius. The Schwarzschild solution revealed a boundary now called the event horizon surrounding the central mass. Any object or light that crossed this boundary would be pulled inexorably inward. The escape velocity at the event horizon equals the speed of light. Since nothing can travel faster than light, nothing that crosses the horizon can escape. The event horizon is a one-way boundary in space-time. For our sun to become a black hole, you'd have to compress all its mass into a sphere about 3 kilometers in radius. For Earth, the Schwarzschild radius is about 9 millimeters. Pack all of Earth's mass into a sphere the size of a grape, and it would collapse into a black hole. Inside the event horizon, all paths lead to the singularity, the point at the center where space-time curvature becomes infinite and our equations break down. Even if you pointed your rocket engines outward and fired them at full thrust, you'd still fall toward the singularity. You could no more avoid reaching the singularity than you could avoid reaching next Tuesday. It's not a place in space you're falling toward. It's a moment in time you're falling into. This is how extreme the warping of space-time becomes inside a black hole. Time and space trade places, in a sense. The singularity is not a point in space, it's a moment in your future that you cannot avoid. Schwarzschild's solution described non-rotating black holes. But in 1963, New Zealand mathematician Roy Kerr found a solution for rotating black holes, and this is where things get even stranger. A rotating black hole drags space-time around with it. Imagine space-time as a fluid, and the black hole as a spinning ball bearing in that fluid. The rotation of the black hole creates a kind of whirlpool in space-time itself. This region, called the ergosphere, extends outside the event horizon. Inside the ergosphere, space-time itself is rotating so fast that nothing can remain stationary. Everything must rotate around the black hole, dragged along by the spinning space-time. But here's the truly bizarre part. The Kerr solution contains mathematically closed timelike curves. These are paths through space-time that loop back on themselves in time. Follow such a path, and you'd return to an earlier moment in your own history. In theory, deep inside a rotating black hole, beyond the outer event horizon and the inner Cauchy horizon, there exist regions where you could, in principle, travel along a path that would bring you back to your own past. Before you get too excited, there are several enormous problems with this. First, the interior of a rotating black hole is almost certainly unstable. The Cauchy horizon, which marks the boundary of the region containing closed timelike curves, is thought to be a place where quantum effects would create an infinitely intense mass inflation that would destroy anything attempting to pass through it. The idealized mathematical solution probably doesn't match physical reality. Second, even if the interior were stable, you'd have to cross the outer event horizon to get there. Once you cross that boundary, you can never escape back to the outside universe. Any closed time-like curves inside the black hole would let you revisit your own past, but only your past after you entered the black hole. You couldn't travel back to a time before you crossed the horizon. Third, and perhaps most fundamentally, regions of space-time containing closed time-like curves may simply not exist in nature. They appear in some exact solutions to Einstein's equations, but those solutions make unrealistic assumptions. They might be mathematical curiosities rather than physical possibilities. Nevertheless, black holes remain the most extreme examples we know of how gravity can warp time. When we detect gravitational waves from merging black holes, ripples in space-time itself, caused by the incredibly violent collision of two black holes, we're observing the most extreme warping of space-time that nature produces. In those final moments before merger, the black holes are orbiting each other at significant fractions of light speed, in regions where space-time is warped almost beyond comprehension. The signals we detect allow us to test Einstein's predictions in the strongest gravitational fields that exist. The 2014 film Interstellar famously depicted a scene near a supermassive black hole called Gargantua. The protagonists land on a planet orbiting very close to the black hole's event horizon. Due to extreme gravitational time dilation, 1 hour on the planet's surface equals 7 years for their colleague waiting on a spacecraft farther away. This wasn't Hollywood exaggeration. The film's scientific consultant, physicist Kip Thorne, carefully calculated what such a scenario would actually look like. For the depicted time dilation to work, the planet would need to be orbiting extraordinarily close to a rapidly spinning black hole, close enough that it would be challenging to maintain a stable orbit, but the physics checks out. The math is real. Near a black hole massive enough and spinning fast enough, 1 hour really could equal 7 years. Black holes are nature's most extreme demonstrations that time is not absolute. Near them, time warps to such degrees that our everyday intuitions completely fail. They show us that the universe permits time to be bent, compressed, dilated to almost arbitrary degrees. But can time be navigated? Can we find shortcuts through it? For that, we need to explore an idea even more exotic than black holes themselves. We need to talk about wormholes. Picture a piece of paper. On this flat sheet, draw 2 dots, one near the top edge and one near the bottom edge. Imagine these dots represent 2 distant locations in space, Earth and a star system, 20 light years away, perhaps. If you were an ant walking on the surface of the paper, traveling from one dot to the other, you'd have to traverse the entire distance between them. But now, fold the paper, bring the 2 dots close together so they're almost touching. Now the ant has a choice. It can take the long route across the surface of the paper, or it can take the shortcut through the tunnel, the wormhole, and arrive at its destination almost instantly. This is the basic idea of a wormhole in spacetime. If spacetime can be curved and folded, and Einstein's general relativity tells us it can, then perhaps regions separated by vast distances could be connected by a shortcut through a higher dimensional space. Instead of traveling the long way through normal spacetime, you could take a wormhole, a tunnel, a shortcut, and arrive at a distant location in far less time than light would take to traverse the intervening space. The first hint of this possibility came from Einstein himself, though he didn't recognize it as such. In 1935, Einstein and his assistant Nathan Rosen were studying the mathematical properties of black holes. They looked at the Schwarzschild solution, the one that described a static, non-rotating black hole, and found something peculiar in its mathematical structure. The equations seemed to describe not just a single region of spacetime, but 2 separate regions connected by a bridge. This bridge, now called an Einstein-Rosen bridge, connects 2 mouths through a throat. You could imagine entering one mouth, traveling through the throat, and emerging from the other mouth in a completely different region of spacetime. There was just one problem, and it collapses fast, incredibly fast. In the idealized Schwarzschild geometry, if you tried to send even a single photon, a particle of light, through an Einstein-Rosen bridge, the bridge would collapse before the photon could make it through. The throat pinches shut so quickly that nothing, not even light traveling at its maximum possible speed, can traverse the wormhole before it closes. The Einstein-Rosen bridge is non-traversable. It's a mathematical curiosity, a feature of the equations, but not something you could actually use to travel anywhere. For decades, that was that. Wormholes appeared in the mathematics of general relativity, but they were useless. Interesting to theorists, perhaps, but of no practical significance, not even hypothetically. Then, in 1988, something unexpected happened. Physicist Kip Thorne received a call from his friend Carl Sagan. Sagan was writing a science fiction novel, Contact, which would later become a film, and he needed a scientifically plausible way to get his protagonist across the galaxy quickly. He asked Thorne, "Could wormholes work for interstellar travel?" Thorne, intrigued, worked with his graduate student Michael Morris to find out. What they discovered was remarkable. Yes, stable, traversable wormholes were possible. Not in the sense of being easy or practical, but in the sense that they didn't violate the known laws of physics. The Morris-Thorne wormhole, as it came to be called, would have two mouths connected by a throat. Unlike the Einstein-Rosen bridge, this throat wouldn't collapse. It would remain open, stable, traversable. You could send light through it. You could send information. You could, in principle, send a person. The geometry would look something like this. Imagine a tube connecting two spherical openings. Each opening exists in normal space. They could be in the same region of the universe or vastly separated. The throat is the shortcut, the tunnel through space-time that connects them. If you looked into one mouth of the wormhole, you'd see through to the region of space around the other mouth. Light could travel through the wormhole in both directions. The journey through the throat might be arbitrarily short. You could cross from one mouth to the other in seconds, even if the mouths were separated by thousands of light years through normal space. This sounds almost too good to be true, doesn't it? A shortcut through the universe, allowing instantaneous or near instantaneous travel across vast cosmic distances. A tunnel that bypasses the light speed limit by going around it rather than through it. What's the catch? The catch is exotic matter. To keep a Morris-Thorne wormhole open and stable, you need something extraordinary filling or lining the throat. You need matter or energy with a very particular property: negative energy density. In normal matter, energy density is positive. A kilogram of iron has positive mass energy. A photon of light has positive energy. Everything we encounter in daily life, every particle and field we know about, has positive energy density. And positive energy density creates gravity. It attracts, pulling space-time inward. A wormhole throat wants to collapse for the same reason a tunnel wants to cave in without support. The curvature of space-time tries to pinch it shut. To keep it open, you need something that pushes outward instead of pulling inward. You need something with negative energy density. Negative energy would create a kind of anti-gravity, not pushing objects away, but curving space-time in the opposite direction from normal matter. It would push outward on the throat of the wormhole, holding it open against the natural tendency to collapse. How much negative energy would you need? That depends on the size of the wormhole and the length of its throat, but the estimates are daunting. For a wormhole large enough to send a human through, say, a few meters in diameter, you might need the negative mass energy equivalent to a planet or a star or more. And here's the really problematic part. We have no idea how to create or collect negative energy in macroscopic quantities. In fact, until the late 20th century, physicists weren't even certain that negative energy could exist at all. But then quantum mechanics offered a glimmer of hope. It turns out the universe does allow negative energy in very specific, very constrained circumstances. Quantum field theory permits regions where the energy density is negative relative to the vacuum. The most famous example is the Casimir effect. In 1948, Dutch physicist Hendrik Casimir made a strange prediction. Take two perfectly conducting metal plates and place them parallel to each other in a vacuum, very close together but not touching. What happens? According to quantum field theory, even empty space, the vacuum, is not truly empty. It's filled with quantum fluctuations, virtual particles constantly popping in and out of existence, borrowing energy from the vacuum for infinitesimally brief moments before disappearing again. The vacuum seethes with activity at the quantum level. These quantum fluctuations include electromagnetic waves of all possible wavelengths. In normal empty space, all wavelengths are present, and on average, the energy density is zero. But between the two conducting plates, something different happens. The plates impose boundary conditions on the electromagnetic field. Wavelengths longer than the separation between the plates cannot exist in the gap. The plates exclude certain quantum fluctuations. Outside the plates, all wavelengths are present. Between the plates, some wavelengths are missing. This creates an imbalance, a difference in quantum vacuum energy density between the region inside the plates and the region outside. The result is that the plates experience an attractive force. They're pushed together by the difference in vacuum energy. And here's the key point. The Casimir effect predicts negative energy. For decades, this was just a theoretical prediction. But in 1997, physicist Steve Lamoureux at the University of Washington measured the Casimir force between a conducting sphere and a flat plate. The measured force matched Casimir's prediction with remarkable precision. Negative energy exists. It's real. We've measured it. Could we use the Casimir effect to stabilize a wormhole? This was the idea that Morris and Thorne, and many physicists since, have explored. If you could somehow arrange exotic matter or fields, perhaps using the Casimir effect or similar quantum phenomena, to create negative energy density in the throat of a wormhole, you might be able to hold it open. The problem is one of scale. The Casimir force between two plates, 1 micrometer apart, about 1/100th the width of a human hair, is absolutely tiny. At that separation, the force is about 0.013 pascals per square centimeter. That's roughly the pressure exerted by a sheet of paper resting on a table. To stabilize a wormhole large enough for a human to pass through, you'd need negative energy densities, many orders of magnitude larger than what the Casimir effect can produce. You'd need to scale up the effect from the quantum realm to the macroscopic realm, and we have no idea how to do that. Moreover, the Casimir effect produces negative energy only in a very specific configuration between the plates. To thread a wormhole throat, you'd need to arrange your exotic matter in a very particular way, and it's not clear that the Casimir effect could be configured to do that. Some researchers have proposed more exotic arrangements. Perhaps you could use dynamic Casimir effects, where moving boundaries create negative energy regions. Perhaps quantum field effects in curved spacetime could produce the necessary negative energy. There's even a naturally occurring form of negative energy already present throughout the universe: dark energy. Dark energy is the mysterious substance or field that's causing the expansion of the universe to accelerate. We don't know what dark energy is, but we know it behaves as if it has negative pressure. It pushes outward, causing space itself to expand faster and faster. The equation of state for dark energy suggests it has properties similar to exotic matter. It permeates all of space. It exerts negative pressure. Could dark energy be used to stabilize a wormhole? Could there be some way to concentrate or manipulate it? No one knows. We barely understand what dark energy is, let alone how to manipulate it. But it's tantalizing that the universe already contains something with exotic properties on cosmic scales. Other theoretical frameworks offer different possibilities. In some versions of string theory, which describes the universe as containing extraspatial dimensions beyond the three we experience, wormholes might be stabilized by effects from these higher dimensions. In modified theories of gravity, where Einstein's equations are altered in specific ways, the exotic matter requirements might be reduced or eliminated. But as of now, in the physics we know and understand, creating a macroscopic, traversable wormhole seems to require amounts of exotic matter we have no idea how to obtain. And even if we could solve the exotic matter problem, wormholes create another issue, one that's even more fundamental than engineering challenges. They create paradoxes, because a wormhole isn't just a shortcut through space. Under certain circumstances, it could be a shortcut through time. Imagine you build a time machine. You step into it, set the controls for 50 years in the past, and activate the device. Moments later, you step out into the world of decades ago. You walk down a familiar street, but the cars are different, the buildings are different, everything is different because you're in the past. You locate your grandfather. He's young, perhaps in his 20s, not yet married to your grandmother. And then for whatever reason, let's not worry about the motivation you prevent him from meeting your grandmother. Maybe you cause an accident that sends him to a different city. Maybe you convince him to join the military instead of attending the college where he would have met her. The exact mechanism doesn't matter. The point is, your grandfather never meets your grandmother. They never fall in love. They never marry. They never have children. One of those children would have been your mother or father, but now that child will never be born, which means you will never be born. But if you were never born, you couldn't have traveled back in time to prevent your grandparents from meeting. But if you didn't prevent them from meeting, then you would be born, and you could travel back in time and prevent them from meeting, but then you wouldn't be born. You see the problem? This is the grandfather paradox, the most famous of all time travel paradoxes. It's a logical contradiction that seems to make time travel to the past impossible. How can you exist to prevent your own existence? How can an effect, your non-existence, eliminate its own cause, your interference in the past? The grandfather paradox, in its various forms, has been a staple of science fiction since the 1920 seconds. It's been explored in countless stories, novels, and films. Back to the Future famously depicted Marty McFly beginning to fade from existence as his actions in 1955 threatened to prevent his parents from falling in love. But this isn't just a science fiction problem. If time travel to the past is physically possible, if wormholes or other mechanisms allow backward time travel, then physics must somehow deal with these paradoxes. The paradox can take many forms. The Hitler paradox asks what would happen if you went back in time and killed Adolf Hitler before he rose to power. You'd prevent World War II and the Holocaust, which seems like a good thing, but you'd also eliminate your reason for traveling back in time. If World War II never happened, why would future you decide to go back to stop Hitler? Without that motivation, you wouldn't make the trip. Hitler would rise to power, World War II would happen, and future you would decide to go back and stop him. Another loop of contradiction. Physicist Joseph Polchinski devised a particularly clean version of the paradox. Imagine a wormhole with two mouths. You fire a billiard ball toward one mouth at just the right angle. It enters the wormhole and emerges from the other mouth in the past. It emerges at just the right time and place to collide with its earlier self before it entered the first mouth, knocking it off course so it never enters the wormhole. But if it never enters the wormhole, it can't emerge in the past to knock itself off course. But if it doesn't get knocked off course, it does enter the wormhole, emerges in the past, and knocks itself off course. The paradox doesn't require malicious intent or complicated human motivations. It's a pure consequence of allowing backward causation, allowing effects to precede and prevent their causes. How does physics resolve this? Or can it? There are several proposed solutions, each with its own implications for the nature of reality, free will, and time itself. Let's explore them, one by one, and see if any can save time travel from its own contradictions. The first proposed solution is perhaps the most elegant: the Novikov self-consistency principle. In the late 1980 seconds, Russian physicist Igor Novikov proposed that if time travel is possible, then only self-consistent events can occur. The universe, in effect, forbids paradoxes, not by making time travel impossible, but by making paradoxical events impossible. Under this principle, you could travel to the past, you could interact with it, you could even try to kill your grandfather, but something would always prevent you from succeeding. Your gun would jam. You'd trip at the critical moment. a stranger would intervene. Your grandfather would inexplicably survive what should have been a fatal accident. The laws of physics, the probabilities of quantum mechanics, the random chances of everyday life would all conspire to ensure that history plays out exactly as it always did, including your presence in the past. This doesn't mean you lack free will. It means your free will is constrained by consistency. You're free to try anything you want, but the universe ensures that what you try is compatible with the future you came from. Think of it this way. If you succeeded in preventing your own birth, then there would be no future you to travel back in time. But since you did travel back, since you are there in the past, then logically, you must fail in any attempt to prevent your existence. Your presence in the past is proof that history is self-consistent. Polchinski's billiard ball paradox has self-consistent solutions. Calculations show that the ball could enter the wormhole, emerge in the past, and deliver a glancing blow to its earlier self. Not enough to prevent it from entering the wormhole, but enough to alter its trajectory slightly. The altered trajectory causes it to enter the wormhole at a slightly different angle, emerge in the past with a different trajectory, deliver the same glancing blow, and the whole cycle repeats consistently. No paradox, no contradiction, just a strange, looping, but perfectly self-consistent timeline. The Novikov principle has a certain appeal. It preserves the possibility of time travel while eliminating paradoxes through a kind of cosmic censorship. The universe protects its own consistency, but it has a troubling implication. If the Novikov principle is correct, then in a very real sense, your actions in the past are predetermined, not because of fate or destiny, but because of logical necessity. The past has already happened from the future's perspective, so your actions in the past must be compatible with that already determined history. Another proposed solution takes a completely different approach. The many worlds interpretation of quantum mechanics. In standard quantum mechanics, when a quantum system is measured, it collapses from a superposition of multiple possible states into a single definite state. The many worlds interpretation, proposed by physicist Hugh Everett in 1957, suggests something different. The universe doesn't choose one outcome. Instead, all possible outcomes occur. When you measure a particle's spin and get up, there's another branch of reality where you measured it and got down. The universe splits into multiple parallel timelines, one for each possible quantum outcome. Applied to time travel, this offers an elegant solution to the grandfather paradox. You travel to the past and prevent your grandparents from meeting. In doing so, you don't change your own timeline. You create a new timeline, a parallel branch of reality. In that branch, you're never born. But you came from a different branch, one where your grandparents did meet, where you were born, where you built a time machine. You haven't changed the past. You've created an alternate past. There's no paradox because you're not preventing your own existence. You're preventing the existence of an alternate version of yourself in a different timeline. You exist because in your timeline, no one traveled back to prevent your grandparents from meeting. The many-world solution is appealing in its own way. It preserves time travel, eliminates paradoxes, and doesn't require the universe to conspire to prevent certain actions. You're free to do anything you want in the past, and the universe accommodates it by branching into a new timeline. But it has its own troubling implication. It requires that the universe constantly splits into countless parallel realities, most of which you can never access or observe. It raises philosophical questions about identity. Is the version of you in the alternate timeline really you? It seems less like traveling to your past and more like traveling to a different universe that resembles your past. Then there's Stephen Hawking's approach, chronology protection. In 1992, Hawking proposed what he called the chronology protection conjecture. He suggested that the laws of physics conspire to prevent the formation of closed timelike curves, loops in time that would allow backward time travel, not as a fundamental law, but as an emergent consequence of quantum effects in curved spacetime. Here's the idea. Imagine you're trying to build a time machine, perhaps by manipulating a wormhole to create a closed, timelike curve. As you bring the configuration closer and closer to allowing time loops, quantum vacuum fluctuations would become amplified. The vacuum energy density near the forming closed timelike curve would spiral toward infinity, creating what's called a quantum divergence. This divergence would likely destroy the time machine before it could function. The very act of creating a closed timelike curve would trigger quantum effects violent enough to prevent its formation. Hawking famously said the chronology protection conjecture is what keeps the world safe for historians. Is it true? We don't know. We'd need a complete theory of quantum gravity, a theory that unifies quantum mechanics and general relativity to say for certain. Such a theory doesn't exist yet, but calculations in semi-classical gravity, treating spacetime classically, but matter quantum mechanically, suggest Hawking might be right. More recently, in January 2025, physicist Lorenzo Gavesino at Vanderbilt University proposed yet another mechanism for preventing paradoxes, this one based on thermodynamics. His work, published in the journal Classical and Quantum Gravity, showed that the behavior of entropy, the measure of disorder in a system, changes fundamentally on a closed timelike curve. Normally, entropy increases, and this increase defines the arrow of time, the direction from past to future. But on a time loop, quantum fluctuations could cause entropy to decrease, effectively reversing processes. What would this mean for a time traveler? As you loop through time, your memories might spontaneously erase. Your aging might reverse. Any action you took might spontaneously undo itself. The very process of creating a paradox might trigger thermodynamic effects that prevent the paradox from persisting. You could travel through time, but you couldn't retain the memories or physical changes that would allow you to create a contradiction. The universe would use thermodynamics to enforce consistency. Each of these proposed solutions, Novikov's self-consistency, many worlds branching, Hawking's chronology protection, Gavesino's thermodynamic erasure, offers a different way for the universe to handle the seeming contradictions of time travel. None are proven. All remain theoretical. But together, they suggest that even if time travel to the past is possible, the universe has multiple mechanisms to prevent paradoxes from destroying causality. The laws of physics seem to protect themselves. But how, exactly, would you create a time machine in the first place? We've talked about wormholes, but there are other proposed mechanisms, some even more exotic. Let's explore what modern physics says about the actual engineering of time travel. In 1949, the great logician Kurt Gödel, the same mathematician who proved the incompleteness theorems that revolutionized logic, discovered something remarkable hidden in Einstein's equations. Gödel was a close friend of Einstein. They worked at the Institute for Advanced Study in Princeton and often walked home together, discussing physics and philosophy. For Einstein's 70th birthday, Gödel decided to give him an unusual gift, a new solution to the field equations of general relativity. Gödel's solution described a rotating universe, one where all the matter in the cosmos rotates relative to the distant stars. In such a universe, space-time itself would be twisted by the rotation in a way that creates closed timelike curves. In Gödel's rotating universe, you could travel in what seems like a spatial loop, flying a spaceship in a large circle through space, and arrive back at your starting point before you left. You'd complete the loop and meet your earlier self. The closed timelike curve in Gödel's solution doesn't require exotic matter or wormholes. It's just a property of the geometry of a rotating universe. The rotation drags spacetime around in such a way that if you go far enough, fast enough, in the right direction, your future light cone tilts back and intersects your past. Fortunately or unfortunately, depending on your perspective, Our universe doesn't rotate in the way Gödel's solution requires. Observations of the cosmic microwave background and the large-scale structure of the universe show no evidence of overall rotation. Gödel's solution is mathematically valid, but it doesn't describe our reality. Still, it proved something important. Einstein's equations permit closed, timelike curves. Time travel to the past is not forbidden by general relativity itself. Another proposed mechanism is the Tipler cylinder, described by mathematical physicist Frank Tipler in 1974. Imagine an infinitely long, infinitely dense cylinder rotating at nearly the speed of light. The rotation would drag space-time around the cylinder in a phenomenon called frame dragging. If you flew your spaceship in a helical path around the cylinder, following the dragged space-time, you could complete a loop that brings you back to your own past. The Tipler cylinder would create closed, time-like curves in the region surrounding it. The problems with this are obvious: infinite length, infinite density, near light speed rotation. These aren't engineering challenges, they're fundamental impossibilities. You can't have an infinite object in a finite universe. You can't rotate something infinitely dense without it immediately collapsing into a black hole. The Tipler cylinder is a mathematical curiosity that shows closed time-like curves are possible in principle, but it's not something that could exist in reality. Then there are the closed time-like curves potentially lurking inside rotating black holes. We mentioned these earlier. The Kerr solution to Einstein's equations describes a rotating black hole with strange properties in its interior. Beyond the event horizon, beyond an inner horizon called the Cauchy horizon, there exists a region where closed time-like curves are possible. But accessing this region would require surviving the journey through the black hole's interior, including passage through the Cauchy horizon, where most physicists believe quantum effects would create an impassable barrier of infinitely blue-shifted radiation. And even if you could reach the region with closed time-like curves, you'd be trapped inside the black hole's event horizon, unable to send information back to the outside universe. These solutions, Gödel's rotating universe, the Tipler cylinder, the interior of a Kerr black hole, are sometimes called proof-of-principle solutions. They prove that general relativity allows closed, time-like curves, but they don't provide a practical path to building a time machine. For that, physicists have looked to wormholes. Not just any wormholes, but wormholes manipulated in a very specific way. Here's how it could work. Start with a traversable wormhole somehow stabilized with exotic matter. Both mouths existing in the same region of space, separated by perhaps a few meters. For now, traveling through the wormhole doesn't take you through time. It just takes you from one mouth to the other, a distance of a few meters. Now take one mouth of the wormhole and accelerate it to a high velocity, say, a significant fraction of the speed of light. Keep the other mouth stationary. Because of time dilation, time passes more slowly for the moving mouth than for the stationary mouth. After the moving mouth has traveled at high speed for a while, bring it back and place it near the stationary mouth again. The two mouths are now out of sync in time. The stationary mouth is older than the moving mouth. It has experienced more time. Now, if you enter the stationary mouth, you travel through the wormhole and emerge from the moving mouth, which is younger, which exists in the past relative to the stationary mouth. You've traveled backward in time. The time difference would be limited by how much time dilation you could create, how fast and how far the moving mouth traveled. But in principle, this would create a time machine, a wormhole time machine. The catch, of course, is that you need a traversable wormhole to start with, which requires exotic matter. And you need to accelerate one mouth of the wormhole to relativistic speeds, which requires enormous energy. And you can't travel back to a time before the time machine was created. The wormhole can only take you back to moments after the time difference between the mouths was established. Still, this shows how combining wormholes with time dilation could create a time machine without requiring rotation, infinite cylinders, or plunging into black holes. Which brings us to the most speculative modern ideas about time travel. faster than light travel, and its strange connection to backward time travel. In special relativity, there's a deep connection between traveling faster than light and traveling backward in time. To understand this, we need to appreciate what special relativity says about simultaneity. The concept of now. In everyday experience, we think of now as universal. We might not know about distant events immediately because information takes time to reach us, but we imagine there's an objective fact about what's happening right now across the universe. Special relativity shatters this intuition. In relativity, simultaneity is relative. Two events that are simultaneous in one reference frame are not simultaneous in another reference frame moving relative to the first. There's no universal now that extends across space. Now depends on your motion. Here's where it gets strange. If you could travel faster than light, you could exploit this relativity of simultaneity to travel backward in time. Imagine Alice and Bob are far apart in space, both at rest relative to each other. Alice sends a faster than light signal to Bob. From Alice's perspective, the signal arrives at Bob at the same time it was sent, or perhaps shortly afterward it's instantaneous or nearly so. But now consider a third observer, Carol, moving at high speed relative to Alice and Bob. From Carol's perspective, due to the relativity of simultaneity, Bob receives the signal before Alice sent it. If Bob now sends a faster than light signal back to Alice, and if Carol's frame is taken into account, Alice could receive the return signal before she sent the original signal. This is called the tachyonic anti-telephone, a way to send messages backward in time using faster than light signals. If you could travel faster than light, you could, through careful choices of reference frames and travel directions, arrive at your destination before you left, traveling backward in your own timeline. Faster than light travel and time travel are fundamentally linked in special relativity. Achieve one, and you've achieved the other. This brings us to the Alcubierre drive. In 1994, Mexican physicist Miguel Alcubierre proposed a way to achieve faster than light travel without violating the light speed limit. He was inspired by watching Star Trek and wondered whether the warp drive depicted in the show could actually work within general relativity. His solution is ingenious. Instead of accelerating to faster than light speeds through space, the Alcubierre drive warps spacetime itself. It creates a warp bubble, a region of space that contracts in front of a spacecraft and expands behind it. The spacecraft itself remains in a flat region of spacetime inside the bubble. It's not moving through this local space at all, but the bubble is moving through spacetime, carrying the spacecraft with it, and the bubble can move at any speed, including faster than light. From the spacecraft's perspective, everything is normal. No time dilation, no mass increase, no acceleration forces. From an external perspective, the spacecraft is crossing vast distances in short times, potentially traveling from Earth to Alpha Centauri in days or weeks instead of years. The Alcubierre drive seemed almost too good to be true. And, of course, there are catches. First, the mathematics requires negative energy density to create the warp bubble, just like traversable wormholes. The region of contracted space ahead of the ship and the region of expanded space behind it need to be threaded with exotic matter. Estimates for the amount of negative energy vary, but early calculations suggested you'd need the mass energy equivalent of Jupiter in negative form. Subsequent refinements have reduced this requirement dramatically. In 2011, Harold White at NASA's Eagle Works laboratory found that by adjusting the shape of the warp bubble, making it thicker, less like a thin shell, and more like a rounded form, you could reduce the exotic matter requirement by enormous factors. Recent theoretical work by researchers like Alexei Bobrik and Gianni Martire suggests you might need only the mass energy of a small spacecraft in negative form. That's still exotic matter we don't know how to create, but it's a far cry from Jupiter. Second, there's a causality problem. Alcubierre himself noted that his drive could be used to create a time machine. If you can travel faster than light, you can travel backward in time using the tachyonic anti-telephone principle. You can create closed time-like curves. Alcubierre has stated that any method allowing faster than light travel can, in principle, be used to travel back in time. He references Hawking's chronology protection conjecture. Perhaps something in the physics will prevent it from working when configured as a time machine. Perhaps the exotic matter will catastrophically fail, or quantum effects will destroy the bubble, or something else will go wrong. But if chronology protection doesn't save us, then the Alcubierre drive is not just a faster-than-light drive. Third, there are practical problems with steering and operation. You'd need to set up the warp field before getting inside it, and you might not be able to turn it off from inside. The warped spacetime also can't propagate faster than light, so creating the warp field in the first place seems to require faster than light signaling a chicken and egg problem. Despite these issues, research on the Alcubierre drive continues, not because anyone expects to build one soon, but because studying these exotic solutions to Einstein's equations teaches us about the limits of physics, the nature of space-time, and the connection between quantum mechanics and gravity. The fact that such a solution exists, even if only on paper, tells us something profound. The universe's laws don't absolutely forbid faster than light travel. They just make it incredibly, perhaps impossibly, difficult. But what about quantum mechanics? Could the quantum realm offer paths to time travel that relativity alone cannot? At the smallest scales, where quantum mechanics governs reality, time behaves strangely. Quantum mechanics is fundamentally probabilistic. Before you measure a quantum system, it exists in a superposition of multiple possible states. The famous Schrödinger's cat is both alive and dead until you open the box. The electron is in multiple places until you detect it. Measurement causes this superposition to collapse into one definite outcome. But the many worlds interpretation suggests something different. All outcomes occur, each in its own branch of reality. If many worlds is correct, then every quantum measurement splits the universe into multiple parallel timelines. This happens constantly, trillions of times per second, as quantum events throughout the universe resolve into definite outcomes. Could these quantum branchings be related to time travel? In 2010, physicist Seth Lloyd at MIT devised an experiment to test the principles of quantum time travel. He couldn't create an actual time machine, no one can, but he could create a quantum simulation that mimics what would happen if a photon traveled through a closed time-like curve. Lloyd used the principles of quantum teleportation, a process where quantum information is transferred from one location to another using entangled particles to simulate the effect of a photon going through a wormhole, backward in time, and interacting with its past self. The key addition was post-selection, a technique that allows you to select only certain outcomes of a quantum process. This effectively made the simulation deterministic rather than probabilistic. The results were striking. The simulated photons behaved in a way consistent with the Deutsch-Polchinski solution to the grandfather paradox. When a photon was set up to potentially create a paradox to prevent its past self from entering the time loop, the quantum probabilities adjusted themselves to prevent the contradiction. The photons couldn't create paradoxes. The quantum mechanical setup ensured consistency. This doesn't prove that macroscopic time travel is possible, but it suggests that quantum mechanics has built-in mechanisms to prevent paradoxes. The probabilistic nature of quantum mechanics might be what saves causality. In 2014, researchers at the University of Queensland performed a similar experiment, creating a quantum simulation of closed time-like curves. They sent photons through an optical setup that mimicked the topology of a time loop. Again, the results showed that quantum mechanics naturally enforces consistency. Paradoxes were prohibited not by conscious intervention or luck, but by the structure of quantum probability itself. These experiments hint at something profound. If time travel is possible, Quantum mechanics might be what makes it work without breaking causality. There's another quantum connection to consider: the relationship between wormholes and quantum entanglement. In 2013, physicists Juan Maldacena and Leonard Susskind proposed the ER equals EPR conjecture. ER refers to Einstein-Rosen bridges, wormholes. EPR refers to Einstein-Podolsky-Rosen entanglement, the quantum phenomenon where two particles remain connected regardless of distance, such that measuring one instantly affects the other. The ER equals EPR conjecture suggests these two phenomena are actually the same thing. When two particles are entangled, they're connected by a tiny, non-traversable wormhole in spacetime. Quantum entanglement and wormholes are two descriptions of the same underlying geometry. If this is true, it connects the quantum realm to the structure of spacetime in a deep way. It suggests that spacetime itself might be woven from quantum entanglement, that the fabric of space and time emerges from quantum connections between fundamental constituents. What does this mean for time travel? We don't fully know yet, but it hints that understanding time travel might require understanding quantum gravity, a theory that unifies quantum mechanics and general relativity. Several approaches to quantum gravity exist. String theory, which describes particles as tiny vibrating strings in higher dimensional space, allows for exotic topologies that might include traversable wormholes or closed timelike curves. Loop quantum gravity, which describes spacetime as composed of discrete quantum loops, suggests that time itself might be emergent rather than fundamental. In some of these theories, time is not a basic feature of reality. Instead, time emerges from more fundamental quantum processes. If time is emergent, then traveling through time might mean something very different from what we imagine. Perhaps more like reconfiguring the quantum state of the universe than moving along a temporal dimension. We're far from having a complete theory of quantum gravity, but hints from quantum mechanics suggest that if time travel is possible, it will be intimately connected to the quantum nature of reality. The marriage of quantum mechanics and relativity might hold the key to understanding whether the past and future are truly accessible, or whether time's arrow points in only one direction, not as a law of physics, but as a consequence of deeper quantum principles. So, where does this leave us? What does modern physics really say about time travel? Let's take stock. We've journeyed through Einstein's relativity, through black holes and wormholes, through paradoxes and their proposed resolutions, through faster-than-light theories and quantum mechanics. What can we say with confidence? First, time dilation is absolutely real. This is not speculation or interpretation. It's measured fact, confirmed in hundreds of experiments. Clocks at different altitudes tick at different rates. Particles traveling at high speeds live longer than stationary particles. In 1971, the Haffley-Keating experiment flew atomic clocks on commercial airplanes around the world, confirming that clocks in motion and at different altitudes ticked at different rates than stationary clocks on the ground. GPS satellites must correct for time dilation or they'd fail within hours. Time is not absolute. It flows at different rates depending on velocity and gravitational field. This is established physics, as solid as any scientific fact we possess. Second, the mathematics of general relativity permits wormholes and closed timelike curves. These solutions are mathematically valid. Einstein's theory doesn't forbid them, but, and this is crucial, mathematical validity doesn't guarantee physical existence. Just because something appears in the equations doesn't mean it can exist in nature. The equations might describe idealized scenarios that reality doesn't permit. The math might require initial conditions or material properties that the universe doesn't allow. The key question is exotic matter with negative energy density. We know negative energy exists at quantum scales. The Casimir effect proves it. We've measured it, but the amounts involved are minuscule, and they appear only in very specific configurations. Scaling up the Casimir effect, or similar quantum phenomena, to macroscopic amounts enough to stabilize a traversable wormhole or power an Alcubierre drive, is a challenge we have no idea how to meet. It might be possible in principle. It might be forbidden by deeper principles we don't yet understand. Some theoretical work suggests the amount of exotic matter needed might be reducible. Modified theories of gravity, higher dimensional physics, or clever geometric configurations might lower the requirements. But we're still talking about forms of matter and energy we can't create and barely understand. Then there's the causality problem. Even if we could create a wormhole or a warp drive, even if we solved the exotic matter problem, we face the deeper question. Does the universe permit closed time-like curves in practice? Hawking's chronology protection conjecture suggests no. The conjecture states that whenever you try to create a configuration allowing time travel to the past, quantum effects will intervene to prevent it. Vacuum fluctuations will amplify. Energy densities will diverge. Something will break before the time machine can function. This conjecture isn't proven. It's not a theorem. We'd need a complete theory of quantum gravity to be certain. But calculations in semi-classical gravity support it. When physicists model the quantum vacuum near forming closed time-like curves, they find instabilities that seem to destroy the time machine. Nature might have a built-in safety mechanism, a cosmic sensor that forbids time travel not by fundamental law, but by ensuring that any attempt to create a time machine triggers its own destruction. Alternatively, if Novikov's self-consistency principle is correct, time machines might be possible, but paradoxes are impossible. The universe would permit time travel while enforcing logical consistency through quantum probabilities or classical constraints. Or if many worlds is correct, time travel might create new timelines rather than changing existing ones, eliminating paradoxes by separating causes from effects across parallel realities. We don't know which, if any, of these solutions is correct. What we can say is this: time travel to the future is easy, proven. Accelerate to high velocity or position yourself in a strong gravitational field, and you'll travel into the future faster relative to others. This is not only possible, it's unavoidable. Time travel to the past is permitted by the mathematics of general relativity, but may be forbidden by physics we don't yet fully understand. The obstacles are enormous. Exotic matter requirements, potential chronology protection, paradoxes requiring resolution. No one has identified a plausible path from our current technology and understanding to a working time machine. But, and this is important, no one has proven it's impossible either. The question remains open, tantalizing, frustrating, profound, and perhaps that's appropriate. Because the real value of studying time travel isn't whether we'll ever build a time machine. The real value is what we learn along the way. The quest to understand time travel has led to some of the deepest insights in modern physics. Studying wormholes has taught us about the structure of spacetime, the relationship between topology and geometry, the connections between distant regions of the universe. Grappling with paradoxes has forced us to think carefully about causality, about the nature of physical law, about what it means for events to have a definite ordering. Exploring closed time-like curves has revealed subtle aspects of general relativity, connections to quantum mechanics, hints about the fundamental nature of time itself. Even if time travel turns out to be impossible, the journey toward understanding why it's impossible is valuable. The constraints that prevent time travel might point toward deeper principles that could unlock new physics, new understanding, new technologies we can't yet imagine. But beyond the physics, time travel raises profound philosophical questions. What is time, really? In everyday experience, time seems to flow. The present moment feels uniquely real. The past is gone, fixed, unchangeable. The future is open, uncertain, yet to be determined. But physics doesn't support this view. In relativity, space-time is a four-dimensional block. Past, present, and future all exist simultaneously in the mathematical structure. The flow of time, the sensation that the present moment is special. Some physicists and philosophers embrace this block universe view. They argue that past, present, and future are equally real. The passage of time is an illusion created by our consciousness, by the way our brains process memory and anticipation. We exist at all moments of our lives simultaneously, but our consciousness experiences only one moment at a time, creating the sensation of flow. Others argue for a growing block universe, where the past and present are real, but the future is not yet determined. Or for presentism, where only the present moment is real, the past has ceased to exist, and the future doesn't yet exist. These aren't just abstract philosophical positions, they have implications for time travel. If the block universe view is correct, then the past exists just as solidly as the present. It's out there in space-time, accessible in principle if you can navigate the geometry correctly. But if presentism is correct, if only the present is real, then the past has vanished. There's nowhere to travel to. Time travel to the past would require recreating what has ceased to exist, not navigating space-time but literally rewinding the universe. We don't know which view is correct. Physics doesn't tell us. General relativity describes space-time as a four-dimensional block, but that might be a useful mathematical model rather than an accurate description of reality's fundamental nature. Then there's the question of free will. If you travel to the past, are your actions free, or are they constrained by the requirement of self-consistency? The Novikov principle suggests that if you travel to the past, your actions must be compatible with the history that led to your journey. You're free to act, but the outcomes of your actions are predetermined by consistency requirements. This seems to eliminate free will in the past, not by external force or fate, but by logical necessity. The past has already happened from the future's perspective, so your actions in the past must produce the history you already know occurred. But many worlds offers a different perspective. If your actions in the past create a new timeline, you're genuinely free to act however you choose. There's no constraint, no predetermined outcome. The branching of realities preserves free will while eliminating paradoxes. These questions touch on the deepest issues in philosophy. What is time? What is causation? Do we have free will? What is the nature of reality? Physics has given us new tools to explore these ancient questions, but it hasn't answered them. Perhaps it can't. Perhaps these questions require insights beyond physics, from philosophy, from consciousness studies, from domains of thought that transcend mere mathematics. Or perhaps the answer is that we're asking the wrong questions. Perhaps time is more subtle, more strange, more wonderful than we imagine. Perhaps the universe is structured in ways we haven't conceptualized yet. Future generations might look back at our struggles with time travel and smile, understanding it in ways we can't yet grasp, just as we smile at medieval attempts to understand motion before Newton, or Victorian attempts to understand electricity before Maxwell. The journey continues. The mystery deepens. And that, perhaps, is exactly as it should be. There's something deeply human about the desire to travel through time. We dream of visiting the past, not just to see history, though that's part of it, but to fix mistakes, to say things we didn't say, to spend more time with people we've lost, to choose differently at crucial moments. Knowing what we know now, the past holds our regrets, and we imagine that if we could just go back, just reach into that time that's gone, we could make things right. We also dream of seeing the future. We want to know how things turn out. We want to see the consequences of our choices. We want to know if humanity survives, if we solve our problems, if the arc of history bends toward justice or tragedy. The future holds our anxieties and our hopes, and we imagine that if we could just glimpse it, we could prepare better, choose more wisely, understand our place in the long sweep of time. Time travel has been a staple of fiction for well over a century. H. G. Wells's The Time Machine, published in 1895, set the template, a device that allows travel through time as easily as one travels through space, opening the fourth dimension to human exploration. Since then, countless stories have explored the possibilities and paradoxes. Back to the Future gave us a comedic take on the grandfather paradox, with Marty McFly nearly erasing himself from existence. 12 Monkeys explored the futility of trying to change a predetermined past. Interstellar showed relativistic time dilation in scientifically accurate detail, with emotional consequences as profound as the physics. These stories resonate because they tap into something essential about human consciousness. We are trapped in the present moment. That's not a metaphor. That's a literal description of conscious experience. You cannot experience the past, you can only remember it. You cannot experience the future, you can only anticipate it. Consciousness exists only and always in the now. The present is a knife's edge between past and future. And we're balanced on that edge, moving forward inexorably at the rate of 1 second per second, unable to stop, unable to reverse, unable to skip ahead. Time is our prison. We're locked in the forward flow of causality, able to influence the future, but never the past, able to learn from experience, but never to relive it. Time travel represents freedom from this constraint. It represents power over our greatest limitation, our inability to escape the relentless march of time. It represents the possibility of second chances, of foreknowledge, of breaking free from the linear progression that constrains every moment of our existence. It's no wonder we're fascinated by it. But here's the paradox. The very things that make us long for time travel are the things that would make it meaningless. We want to change the past to fix our regrets. But if we could change the past, we'd eliminate the future that led us to want to change it. Success would erase the motivation for trying. We want to know the future to make better choices. But if we learned the future and changed our choices as a result, we'd change the future we learned, making the knowledge false. Time travel stories often recognize this. The most sophisticated ones explore how time travel doesn't actually give us the control we think it would. The past resists changing. The future remains uncertain even if you've seen it. Knowledge of time creates new problems as often as it solves old ones. Maybe the desire for time travel is really a desire to escape the fundamental nature of existence, the fact that we live in moments that become past as soon as we experience them, that we can never hold on to the present, that we're always moving into an unknown future. Maybe what we really want isn't time travel. Maybe what we want is more time, more presence, more ability to savor the moments we have before they slip away into memory. And that, ironically, is something we can have, not through wormholes or exotic matter or closed timelike curves. You can't revisit the past. You can't skip to the future, but you can experience the present more fully than you might imagine. And in a very real sense, that's the only time travel that matters. So here we are, at the end of our journey through the physics of time travel. What have we learned? We've learned that time is far stranger than common sense suggests. It's not a universal river flowing the same for everyone. It's a dimension of spacetime, flexible and relative, warped by motion and gravity, different for different observers. We've learned that Einstein's equations permit wormholes and closed time-like curves, shortcuts through spacetime, and loops in time that might, in principle, allow travel to the past. We've learned that the obstacles to actually creating such structures are enormous. Exotic matter requirements, potential chronology protection, paradoxes demanding resolution, practical impossibilities that no known technology can overcome. We've learned that the universe seems to protect causality, whether through self-consistency requirements, quantum mechanics, thermodynamic effects, or outright chronology protection. Nature appears to have mechanisms that prevent paradoxes, even if they don't outright forbid time machines. We've learned that the question of time travel is intimately connected to the deepest questions in physics. What is time? What is causation? How do quantum mechanics and gravity unite? What is the fundamental structure of reality? And we've learned that sometimes the value of a question isn't its answer, but where the question leads us. The quest to understand time travel has expanded our knowledge of space-time, black holes, quantum mechanics, thermodynamics, causality. It has forced us to think rigorously about concepts we usually take for granted. It has revealed connections between seemingly disparate areas of physics. Even if we never build a time machine, we've built understanding. And that's what physics is really about, not building devices, but understanding nature. The beautiful thing is that the question remains open. We don't know if time travel to the past is impossible. We know it's hard. We know it requires physics beyond what we currently understand. We know it faces enormous obstacles, but we can't definitively say it will never happen. Future physicists might discover new principles, new forms of matter or energy, new geometries of space-time, new quantum phenomena. Insights we can't predict because we're still learning the rules. Perhaps in 100 years, 1,000 years, 10,000 years, our descendants will look back at this moment and smile at our primitive understanding. Perhaps they'll routinely travel through time in ways we can't imagine. Perhaps they'll understand time as something entirely different from our current conception. Or perhaps they'll prove it's impossible. Either way, the journey of discovery continues. But here's what I want you to remember as you drift towards sleep tonight. You are, right now, traveling through time. Every second, you move 1 second into the future. Inexorably, inevitably, constantly. You're traveling through the fourth dimension at exactly the rate required to experience causality, to have a sense of before and after, to remember the past and anticipate the future. You're navigating space-time, following your world line, the path your existence traces through the four-dimensional geometry of the universe. And this journey, this constant movement through time, is what makes experience possible. Without time, there would be no change, no causation, no consciousness, no existence as we understand it. You are not outside of time, watching it flow. You are woven into the fabric of space-time itself. You are a process, an unfolding, a pattern moving through the dimensions. Your relationship with time is perhaps the most fundamental aspect of your existence. And yes, you're limited to the present moment. You can't go back and fix the past. You can't skip ahead to see the future. You're confined to the ever-moving now. But the now is where life happens. The now is where you can act, choose, experience, exist. The past is memory. The future is possibility. But the present is reality. The present is the only time that's truly yours. So as you lie here, settling into rest, appreciating the strange journey we've taken through wormholes and paradoxes and the mysteries of time itself, remember this: you live in a universe where time is a dimension as real as space, where the past and future might exist as tangibly as distant places, where the mathematics of reality permits loops and shortcuts that boggle the mind. You live in a universe strange enough that time travel might be possible. And you live in a universe mysterious enough that we're still discovering its basic rules, still unraveling its deepest secrets, still learning what reality truly is. That's wonderful. That's humbling. That's exactly as it should be. There are more mysteries in this cosmos than we can solve in a lifetime. More questions than answers. And that's okay. The journey is the point. The questions are as valuable as the answers. The mystery is what makes existence magnificent. So rest now. And tomorrow, when you wake, you'll have traveled several hours into the future, moved forward through time at the stately pace of 1 second per second, adding to your world line, extending your path through space-time. You are a time traveler. We all are. And in a universe this strange, this beautiful, this full of mystery and wonder, that's exactly what we should be. Before I let you drift fully into sleep, I want to say, if this journey through time and relativity resonated with you, if exploring these cosmic mysteries brought you wonder or peace or curious satisfaction, a like would mean the world to me. And if you'd like to travel through more explorations like this, through black holes and quantum mechanics, through consciousness and cosmology, through all the beautiful mysteries the universe holds, consider subscribing. Your support helps me create these journeys, these late-night explorations into the nature of reality. Thank you for traveling through time with me tonight. Rest well. And remember, every moment, you're doing something extraordinary. You're existing in a universe stranger and more beautiful than we ever imagined. Good night.